left over, which is 6.4. So let's look at that problem. After that, move on from first law. So we are looking at steady state flow through a nozzle. Looks like this. And okay, let's see the statement. Again, I have condensed the statement of the problem. Steam enters an insulated nozzle and leaves superheated. Determine the final temperature of the steam and its quality if saturated. And following data is given to you: pressure, temperature, and velocity. Okay. So let's, how would we do this problem? Firstly, what is asked for? Find the temperature of steam and its quality if saturated. So, I mean, the question is redundant, right? Because if you are saying it's saturated, then I know what the quality is, it's 1. So that part of the question is just redundant, completely redundant. I need to find the final temperature of the steam. Okay. Now, first law, again, in the steady state process, because it is insulated, QCV is 0. No heat exchange. By insulated, he means adiabatic. And there's no work done because in a nozzle, you just have air flowing in and out. It's not going to operate any machine or do any kind of work with the surroundings. So that's gone. So your first law is simple. Okay, enthalpy, initial enthalpy, inlet enthalpy, Vi square by 2 is outlet enthalpy. Okay, so you have to find out the inlet and the outlet enthalpy. Okay, so let's look at the inlet. So he says, okay, so 600 kilopascal, that's the condition, and 200 C. So what's that? Which table shall we look at? Let's say we look at the second table. 600 kilopascal. Okay, if you look at the second table, B.1.2, then 600 kilopascal, the temperature is given to be 158.85 degrees Celsius. But in the problem, the temperature is given to be 200. So this can't be right. We will go to the superheated table. Superheated vapor. So it, as he says, it is entering, steam enters an insulated nozzle and leaves superheated. But what is entering in is also superheated. Okay. So let's do that. Look at the 600 kilopascal table, which is B.1.3. In under 600 kilopascal, if you look at 200 degrees, the enthalpy is 2850.12. So that's your inlet enthalpy. And the outlet condition is telling you it is saturated. That means you are right on the edge. Understand? Let me. So what is the trajectory in the PV diagram? So what he's saying is, right? I mean, what he's saying is that you are in a superheated region, and then in the final state you are here. Basically, that's how it's happening. That's the movement in the PV diagram. So you are on the edge. So when you are here, you can look at this table or you can look at the superheated table. So since we find it easier to use a superheated table, we will look at that. But here, you will run into trouble. Because the data given, data says outlet condition is 1500 kilopascal. Where is the table for 1500 kilopascal? In superheated. There is no table.
So it is 150 kilopascals, right?
Sorry?
150 kilopascals, right?
100, 150 or what is it? Converted 0.15, how many megapascal? 1000, right? 2, 3. So 150 is it? Okay, let's check it. So you can use the you can use any of the tables if you are on the edge, if you are saturated, right? So please convert. Is it 150 or 1500? What is it? 150. Okay, if it's 150, then go to the 150 kilopascal table. Is there a 150 kilopascal table? What do you think? Actually, either way you're unlucky. There is no 150 kilopascal table. There is no 1500 kilopascal table. What will you do? You can always go back to B.1.2, right? Because you're right on the edge. So just read off. If you are let's say it's 150, probably it is. Then you can go to B.1.2, right? And you can go to 150 kilopascal. And now in that you have your enthalpy values, right? Which enthalpy value will you take? Which enthalpy value will you take in B.1.2? Will you take the liquid value or the vapor value? What do you think? You're given that the quality is 1, right? So you will take the vapor value because you are on that side. Right? The final case, you have saturated vapor. So you can take saturated vapor value. That's all. So in under 150, the value is 2693.54. Is that clear? So that's all there is in this problem.
Excuse me, sir.
How
How did you that
Yeah.
the work will be 0 in this case?
Actually, why did we even find the outlet enthalpy? You have the formula in front of you, right? Yeah. You found inlet enthalpy, right? And you have Vi square by 2 and Vo square by 2. So you can find outlet enthalpy. What I was trying to find out is the temperature. That you can read off from the table, right? So for 150 kilopascal, the temperature is 111.37. Is that okay?
Excuse me,
Quality
sir.
is what? Yeah.
How did we get work to be equal to 0?
What? Why?
Why did we get work equal to 0?
I don't know what you're to say. I did not understand what you're saying. Why did you get what equal to 0?
Work.
Work. Oh, why is work equal to 0? Yeah, here there is no. See, work is done when you have. Okay, when will work be done? Suppose I put a wheel in front of the water wheel or air wheel, in front of this nozzle. Then what will happen? It will do work, right? Because the air will be pushing the fan blades, and it will be turning something. But here, no work is done. Nothing is done. There's no work done. We are not putting in anything in front of the nozzle. If you are putting something in front of the nozzle, then work will be done. That's all.
Okay, sir.
So there's no exchange of work between the system and the surrounding. That is all. Or the control volume. Okay. So no work is done, and no heat is exchanged either because the steam is entering an insulated nozzle. Okay, so we're done with this. You can find the outlet enthalpy from this formula and temperature from the table. All right, that's all there is. Let's move on then. Now let's say we are looking at the interconversion of heat and work. Okay, so first question is, I would like to transform work into heat. What is the efficiency of this process? Efficiency is 100%. Okay, can be up to 100%. Let's take an example. I have a resistor, which is my system, and it's a part of a circuit, and the resistor is dipped in the ocean, which is a heat reservoir. Now, if I have a switch on here, the current flows and there is conversion of electrical work into heat in the resistor. But that heat is going to be sucked out by the heat reservoir. So finally, end of the day, what happens? There is no change in thermodynamic coordinates of the system because whatever heat enters in flows out. Okay. Now, how long can we do this process? We can do this process essentially indefinitely, as long as I have a functional battery. Right. So, in other words, I can convert electrical work to heat with 100% efficiency indefinitely, as long as I have a functional battery. Or better still, if this was a cyclic process, then I mean, this is, as shown here, is not a cyclic process because here the battery will run out eventually. But let us say it was a process which I could run all the time, then I could keep on and on doing this. I could keep on converting work to heat with 100% efficiency, at least in theory. Now, the question is the reverse. Can I convert, and if I convert heat to work, what is the efficiency? Can that be 100%? Can you convert 100% of heat into work? And this question is the starting point of the second law of thermodynamics. See, as far as first law is concerned, this process from here to here is possible with 100% efficiency, and so is the reverse process, because ultimately it's conversion of energy, and first law says energy is conserved. So I should be able to go front and back with 100% accuracy depending on the setup. So there is no conflict in going in ensuring that this is a 100% efficient process if I only knew the first law. Right? And suppose this, let's say hypothetically that this process was possible with 100% accuracy, efficiency. What kind of world would we live in? Think about it. I mean, it would be an unusual and most extraordinary universe to live in if this was if this process happened with 100% efficiency. Think about it. It would be a most unusual, I mean, it's literally unthinkable kind of universe, because if this was possible, you would literally have a free lunch. You could literally create miracles without doing anything. I'll give you an example. You have a ship in the ocean. Okay. If in our universe this was possible with 100% efficiency, then you could do something like this: create a ship, put it in the ocean, and start moving on its own, going wherever you want. Why? Because the ocean has, in theory, infinite amount of heat. It might be very, very small and minuscule amount of heat, but when you add up, it's a large amount of heat, right? And that heat can be converted to work with 100% efficiency. So great. I will have a mechanism by which I can extract all that heat from the ocean and go wherever I want. Why would I need fuel? Why do you need fuel in a ship? Why do you need fuel? Or you make a car and then you just extract all the heat from the atmosphere, because there is a lot of heat in the atmosphere, what you call waste heat or whatever you call it, right? A lot of heat is being thrown out into the atmosphere. Why don't you just extract that and have a car running? Then you don't need any fuel, right? So it would be an unusual universe indeed if this happened, if this could be done with 100% accuracy. But this cannot be done. That's because you have something called the second law of thermodynamics, which prohibits this from happening with 100% accuracy. Sorry, efficiency. I keep using the word accuracy. Efficiency, thermal efficiency. Okay, so to introduce the second law, this is actually how it was done historically. Because in the 19th century, During the Industrial Revolution, the main focus of engineers and, in a way, scientists was to make more efficient heat engines. That was the main goal, driving goal. And everybody was striving towards 100% efficiency. And what was the process? Of course, you had a boiler or something, like in a steam engine, and you were burning coal, and you were converting that water to steam, and that steam was driving a turbine. So you were converting heat to work, and you wanted that to be 100% efficiency. Everybody wanted that. And there's no reason to believe why you can't have 100% efficiency, because first law of thermodynamics doesn't say anything. It says this is permissible. I can convert 100% from of the heat into work. It is only after a lot of painful experiments they found out that we just are unable to reach 100% efficiency. So people suspected maybe it's just because your design is poor. There's nothing wrong in it because you are still conserving energy. What's wrong in going this way? So it was a mystery until it was clarified by Kelvin and Helmholtz and a lot of other people that this process is the fact that you can't do this process with 100% efficiency is nothing to do with your engine. It has to do with a basic law of nature. Okay, so we start with the heat engine, and we are always considering cyclic processes. So we're not considering processes which are open-ended, because you want your system to run indefinitely, let us say. So you want the process to be cyclic. And when I say heat engine, you may look at it schematically as something like this. On the image on the left. Okay, so there is a high temperature reservoir and there is a low temperature reservoir. So high temperature reservoir could be your boiler with the steam in it. Is the boiler basically at high temperature, and the low temperature reservoir is what? The atmosphere. And what is the working substance? The substance that is going to, in other words, what is your system? Your system is, in this case, steam, because steam is going to be doing all the transfer of energy or exchange of energy or heat. So this is the basic schematic of any heat engine. There are three elements in it. This is the heat exchanged between the system and the high temperature reservoir. This is the work exchanged, and this is the so this is a work exchange between the system and the surrounding, and this is the heat exchange between the system and the low temperature reservoir. There are three basic things. So now, in discussing heat engines and fridges, what we will do is, to avoid confusion with signs, we'll put a mod symbol in front. Okay, so we'll just take the magnitude of these quantities, and when we want to include a sign, we will put the sign in by hand. What is the convention for heat? Convention is, when heat flows into a system, it is positive. When heat flows out of a system, it is negative. So we will put the sign in by hand, just because we know the direction of heat transfer and work exchange, so we don't have to bother about it. I mean, we'll put the sign in by hand. We will not worry about. Yeah. So what is the efficiency of heat engine? What is the efficiency of a heat engine? I'll just be back. Thermal efficiency is defined as how much work is output divided by the heat that is extracted from the high temperature reservoir. It's like the output by the input. Now from the first law, QH minus QL is work done. Remember, it's a cyclic process. So there is no change in internal energy. So du is 0. So plug that in here and you get your efficiency, which is 1 minus mod QL by mod QH. Ideally, you want 100% efficiency. That means you really want no heat rejected to the low temperature reservoir. And this is permissible as per the first law of thermodynamics. However, you have the second law or the Kelvin-Planck statement, which says it is impossible to construct an engine that operating in a cycle will produce no effect other than extraction of heat from a reservoir and the performance of an equivalent amount of work. So this process is impossible because this involves rejection of heat to the low temperature reservoir. What this statement says is you cannot make an engine which takes heat from a high temperature reservoir and converts that heat 100% into work without rejecting any heat to the low temperature reservoir. That is impossible. Of course, this is not obvious, because if you are just an engineer and you're not thinking physically, you'll say that it's just an issue with my design. I should be able to, by putting in a lot of insulating boundaries and making the process incredibly efficient, doing any kind of engineering stunt to ensure that I don't reject any heat to the atmosphere. Whatever heat I am boiling in the boiler, that boiler, whatever heat is generated in the boiler will be transformed 100% into work. But this law says that it is impossible to do that. Okay, so you cannot have this case as per the second law of thermodynamics. Now the same thing can be asked about a fridge or a refrigerator. Right? What a refrigerator do, at least the schematic at the schematic level. So if you look at the image on the right, you have a low temperature. So essentially what has been done in all the arrow directions have been reversed. Now you imagine your freezer over here, the low temperature is over. You want to, if there is an increase in temperature of the freezer, you want to again reduce it. So you want to extract heat out of the low temperature reservoir. For that you have to do some work, and then there is some heat rejected to the high temperature reservoir. Right? So what is the working substance here? It could be a refrigerant. In that problem we saw last time, it was liquid ammonia. That is the working substance. That's doing all the exchange of work and heat. But the point is you have to do some work which will eventually come from electrical work, from the power grid, to transfer the heat from the low temperature reservoir to the high temperature reservoir, right? I mean, suppose you have a universe where this work is zero, then what will happen? Can you think of that kind of a strange world where no work is required to transfer and spontaneously temperature heat flows from a low temperature reservoir to a high temperature reservoir? Can you even think of that situation? Think about it. I have a copper rod between two reservoirs. One is at 1000 degrees, the other one is at 0 degrees. What I find is heat flows spontaneously from the 0 degree reservoir to the 1000 degree reservoir. What kind of universe is that? I mean, that would be pretty interesting, right? I mean, if that could happen, then you could have again something straight out of science fiction. You could go to Antarctica and just sit and outside and relax. What will happen? All the heat from the cold air outside will spontaneously go into your body. Great. So you'll be feeling quite warm. No need to wear any sweater, nothing. That's quite a magical world, right? So again, violating this law will literally send you straight into the world of science fiction. Right? So again, the analogous question here is, there's no efficiency defined here, but you can define a COP, coefficient of performance, which is defined as mod QL by mod W. Why? Because what you want as the output is the amount of heat extracted from the low temperature reservoir. And what is the input? The work done. So ideally what you want is this work to go to 0 and COP should go to infinity. Okay, first law says this is possible. Second law says this is impossible. And what is the statement of second law? There is the Clausius statement of the second law, which says it is impossible to construct a fridge that operating in a cycle will produce no effect other than transfer of heat from a low temperature reservoir to a high temperature reservoir. No effect other than just transfer of heat from low temperature to high temperature. It is impossible to construct a fridge of this type. Okay, so you can see that both these statements of the second law are not positive statements in a way. They are negative statements. They are saying what is impossible to do. They are not saying what is possible. They are not giving you, any kind of constructive suggestion, if you want to put it that way. It's saying this is not possible. That's all. What is not possible? A heat engine, as explained earlier in the Kelvin-Planck statement, and a fridge, as explained in the Clausius statement. Now you can formally prove that the Clausius statement and the Kelvin-Planck statement are equivalent, but that proof is uninteresting. So I will not get into it. So no interest. It's a purely formal proof in mathematical logic to show this equivalence, and it's not of any interest to us. But you can ask another question, that suppose I don't know anything about, engines and fridges. Why should I have a second law statement which depends on my knowing about or us knowing about a fridge and a heat engine? A heat engine and a fridge is just one, device. You could have other devices, right? You don't have to. Why should a fundamental law of physics depend on your knowing something about a device called a fridge or a heat engine? That is a legitimate question to ask. So the answer is that there are alternative definitions of second law which do not depend on you knowing anything about a fridge or a heat engine, and we will do that next week. But historically, these were the first statements of the second law, because the whole effort was directed in the 19th century to making more efficient engines and also fridges, like systems where you wanted to lower temperature. You want to make freezing. You want to make boxes for transporting fish. Right, fish is transported in ice boxes or in refrigerated containers to prolong the life. So you really want efficient, you want refrigerated containers or processes which have very high COP. How about infinite COP? Okay. So there was an attempt in that direction, which is why the first time these laws were stated in terms of refrigerators and heat engines. But this is not the only statement of the second law. There are many statements actually of second law. We will do another statement of second law which is not talking about fridges and heat engines later. Okay. Now I want to talk about a very important concept which was asked by somebody also, right? Somebody asked a question long back. I don't know who that was. The question was about the connection between or relation between quasi-static process and reversible process. Who was that person? Somebody asked the question. I don't know if that person is here or vanished. Is a quasi-static process reversible? I think that was the question. All right. So first I have to define what is a reversible process. So it's as follows. Reversible process is one that is performed in such a way that at the end of the process, both the system and its local surroundings may be restored to their initial state without producing any changes in the rest of the universe. What I mean by rest of the universe, meaning apart from the system, the local surroundings, whatever else is there, that is the rest of the universe. So I have restored the system and the local surroundings to their initial state, and I have ensured there is no change in whatever else is there. No change whatsoever. No change meaning no change in the thermodynamic coordinates. Then the process is reversible. A reversible process is of course an idealization, just like point mass. Point mass is an idealization. There's nothing like a point mass. So you have idealizations in mechanics. Frictionless pulley. What is the meaning of frictionless pulley? There exists no such thing as a frictionless pulley. Or even worse, massless pulley. We used to study massless pulleys. There's no such thing as a massless pulley. So those are all idealizations which help you to some extent to give you an answer, but you will have to make corrections in real life. It's the same thing here. Reversible process and idealization in thermodynamics. All real processes are irreversible. But you can approximate a process to be as reversible as close to reversible as you like. That's all we can say. All right, so that's the reversible process. Now comes the most important point, which I have written here. A reversible process is both quasi-static and non-dissipative. You have to remember that clearly, because that is, if you like, a quantitative means of, instead of writing all this in English, I would much rather write this statement, because this can be quantified. It is, I repeat, a reversible process is both quasi-static and non-dissipative. So if you relax any of these conditions, then process is irreversible. So let's discuss two important notes about this. Firstly, all reversible processes are quasi-static. But the converse is not true in general. Why? Because the process may be dissipative. I hope you understand this important point. All reversible processes by definition are quasi-static, but if you go this way, you will need the process also to be non-dissipative. But what if it is dissipative? Then it's not reversible. Give me an example, simple example, of a process which is quasi-static and not reversible, meaning it's this way is not true. Tell me. Process that is quasi-static but irreversible. Tell me. Now why I'm asking is this, because there is some implicit false understanding that whenever I use the word quasi-static, it's always reversible. No, this process is incorrect in general. So I'm asking for an example where the process is quasi-static but irreversible. Give me an example. Some trivial example, like you don't have to think of very complicated examples.
Free expansion?
Sorry?
Free expansion?
Free expansion, yes, that's correct. But free expansion is not quasi-static, right? So that's worse. You're right. Free expansion is irreversible, and so is Joule-Thomson expansion, throttling process, right? But both those processes are not quasi-static. I'm saying a process is quasi-static. Process is quasi-static but irreversible. Tell me.
So it may not be a thermodynamic process, right? I mean, if it is not like melting of wax, it may be a quasi-static process, but not a reversible.
That is 100. Firstly, it is certainly a thermodynamic process. Why do you say it's not a thermodynamic process?
I mean, not a gas state process.
Okay, so let's say what you are saying is hydrostatic system, right?
Yes.
But I never said that thermodynamics has to only talk about gases and liquids. You can even talk of magnetic systems, right?
Yes.
Say a paramagnet. So thermodynamic coordinates are magnetization and magnetic field, and nothing to do with gases or anything, or pressure or volume or anything. So yeah, it's a thermodynamic system, but I'm saying you give me an example of a process that is for with any system, which is quasi-static but not reversible.
So melting of
Because that's
wax
we are
can be
looking at the reverse direction.
uh, melting of
Melting
wax
of
is
wax, melting of.
it's
Why do you say
quasi-static
melting of wax is okay? But why is it irreversible?
because once it becomes the vapor, then we can't solidify it back uh, in the normal conditions.
I don't see why not. Suppose I was in a container where I could compress a piston back quasi-statically and condense the vapor back to wax. Then what would you say? Suppose this process was occurring in a closed container with a piston, and I can move the piston very, very, very slowly, right? Then I would be able to, in principle, maybe condense all the vapor molecules back into liquid. What's wrong with that? So you actually, it's right in front of you. Look at this line here. The converse is not true in general because process may be dissipative. What about dissipative processes? Let's take a very simple example. You have gas in a piston, right? So far you have discussed only about frictionless piston, but what if there was friction with the wall? Suppose you had a piston with a rough wall, then I can move the piston quasi-statically, very, very slowly, but can I prevent friction? No, there will always be frictional losses now, right? So then this process is quasi-static, but it is dissipative. That means this process is irreversible. As simple as that. Just gas in a piston with a rough wall. That's one example. So that's something to remember. Please remember this, because this will clarify a lot of confusion among what exactly is reversible, what is quasi-static. Well, here it is. Reversible implies quasi-static, but the converse is not true in general. Maybe, but in general it's not true. You have to ensure that the process is non-dissipative. The second point I want to make is about interaction of a system with a heat reservoir. Okay. So what was heat reservoir? Heat reservoir was, we defined it earlier, and definition had something like, there is no change in the thermodynamic coordinates of the reservoir. It can accept or reject an unlimited amount of heat. If you throw any amount of heat in a reservoir, it will accept it, and there will be no change in the coordinates of the reservoir. That was the definition of the reservoir. So this statement is another important thing about reversible processes. Heat entering or leaving a heat reservoir does so reversibly. What I mean is, changes that take place in the reservoir are the same as those which would take place if the same quantity of heat were transferred reversibly. Now this is something worth thinking about. Okay, requires a bit of thought. What you are saying is, if I have a system interacting with a heat reservoir, if I'm doing any heat exchange, say with the heat reservoir, suppose you're throwing out some heat, then as far as the reservoir is concerned, that process is reversible. Now why is that the case? Because even if you throw a huge amount of heat to the reservoir, the change in coordinates of the reservoir are negligible. They're not zero, they are very, very small. Okay, so let me give you a sort of concrete example. Suppose I have 4 joules of heat which I will reject to the reservoir. Now you will tell me that if I immediately, if I from one state to the next state, if I am rejecting 4 joules of heat, that's a large amount of heat, and why should the process be reversible? I don't think it's reversible. I'm just throwing, process might be, I might be doing anything, but the point is, as far as the reservoir is concerned, there are no change in the coordinates of the reservoir, or I should not use the word no change, but negligible change in the coordinates of the reservoir. So the reservoir will say, whether you give me 4 joules of heat or you give me 0.01 joules of heat, Then you give me in the next state 0.01 joules of heat. Then you give me 0.01 joules of heat. And all those processes add up to 4 joules of heat. It's the same for me because there are no change in my coordinates. Effectively, it's something like that. So heat entering or leaving a heat reservoir does so reversibly, because as far as the reservoir is concerned, in the reservoir, there are no changes or there are negligible changes in the thermodynamic coordinates. Okay, so this statement is about heat exchange between a system and a heat reservoir. That takes place reversibly. But that doesn't mean every process is reversible. But I mean, of course, if you are very strict about it, you can say that even a heat reservoir is an idealization, which is true. Heat reservoir is as much an idealization as reversible process is an idealization, because there's nothing like a true heat reservoir. If you are, as I said, the example, if you take an ice cube and throw it into the ocean, it doesn't mean there is zero change in the temperature of the ocean. There is some negligible change in temperature of the ocean. So you can argue that there's nothing like a true heat reservoir. This is an ocean is the approximation to a heat reservoir. That is all you can say. Just as there is no true reversible process. All real spontaneous processes are irreversible. A reversible process is just an idealization. In fact, as is the concept of heat reservoir. But this is just talking about how heat is exchanged between a system and a heat reservoir. That does so reversibly. So I would say, when you see the word reversible and then you ask what is irreversible, it's just the negation of this statement. Okay. The negation of this statement is irreversible process is non-quasi-static or dissipative or both. That's an irreversible process. So if you have any process which is non-quasi-static, example, free expansion or Joule-Thomson expansion, or it could be dissipative, maybe there's a friction somewhere in the system, then you can directly say process is irreversible. That clear? We look at an idealized process called a Carnot cycle, which is very useful because instead of dealing with the details and specifics of different kinds of heat engines and fridges, there are many kinds of heat engines, Stirling engine, Rankine engine, etc. Forget all that. Let's look at an idealization of an engine called a Carnot engine, which operates in a Carnot cycle. So first we need to know what a Carnot cycle is before we talk about a Carnot engine. Okay. So here is a picture of a Carnot cycle. You have studied this earlier. So I'll just go through it quickly. Basically, it's a reversible cycle. Now I've defined what is reversible process. So you know that all the steps in this cycle are reversible. So you will start from point 1. Your working substance is at the temperature of the low temperature reservoir. You can see this is the TL isotherm. Then you will compress the gas adiabatically till it reaches a temperature of TH. Not the gas, I mean here I mean the, okay, gas, because this Carnot cycle is drawn for a real gas, the shape that you typically expect for a real gas. So let's say the working substance is a real gas. We're going to compress it adiabatically till the temperature rises to, temperature of the gas rises to the temperature of the high temperature reservoir at point 2. Then you will allow the gas to expand isothermally. Note, expand isothermally. You expect that if a gas is expanding, its temperature will go down, right? Volume is increasing, temperature is going down. But you want to hold the temperature constant at TH. That means you will permit heat to enter into the gas from the high temperature reservoir. You will extract heat, QH, from the high temperature reservoirs, so as to ensure that the gas temperature is held constant. So this is the isotherm. To hold the temperature constant, you had to bring in heat because you are expanding it. You are expanding the gas. Then you have further expansion, which is reversible and adiabatic, and temperature drops to TL. Then you again compress it isothermally, reversibly isothermally, back to point 1, because You want to hold the temperature at the low temperature reservoir and you're compressing it, temperature of the gas will increase, but you don't want it to increase, so you'll have to throw out heat. QL. Okay, heat QL will be thrown out. So Carnot cycle is an idealized cycle which operates reversibly. Here's one thing, between two reservoirs. This is not the picture of a real cycle. This is an idealized process. Why is it? Because a real cycle would require a series of reservoirs to operate reversibly, not just two reservoirs. We know that, right? I just said that if you really want to say that the temperature of this copper rod has increased from 4 degrees to 5 degrees, it does not mean that I will put the rod in contact with a 5 degree of, with a higher temperature reservoir, and the temperature will increase instantly or in one step from 4 degrees to 5 degrees. That's not what you will do, because you want the process to be quasi-static. So you will say, I will put the rod in touch with a reservoir of temperature 4.01 degrees Celsius. Then I'll wait for the rod to reach 4.01 degrees Celsius. Then I'll put the rod in contact with the reservoir at temperature 4.02 degrees Celsius. And I'll keep doing that until I reach 5 degrees. That means I have put the rod in contact with infinite number of reservoirs between 4 degrees and 5 degrees. Right? So that's not what is being done over here. This is a one-step process. You're going from TL to TH. There's no other reservoir. There are only two reservoirs, a high temperature and low temperature, which is an idealization. Okay. Yeah, so this Carnot cycle is useful because all the essential features of any engine or fridge can be explained with this one single cycle. The essential processes internal to a fridge or an engine can be explained, the essential processes can be explained using a Carnot cycle. Okay, now you are used to seeing a picture of Carnot cycle that look like that, but actually the picture of a Carnot cycle depends on the working substance shape. Okay, so I've shown you two other Carnot cycles here, so you don't think that Carnot cycle always looks like what it was shown in the previous slide. Carnot cycle shape depends on the working substance, also depends on the thermodynamic coordinates. Okay, so you see here, for example, this is how a Carnot cycle looks for situation where V3 by V1 is 3 halves, and the working substance is an ideal gas. Looks quite distorted, right? But this is also a Carnot cycle. And what about this one? This is the Carnot cycle in the liquid vapor coexistence region. This one is interesting because you can see this process 2,3 is isobaric, and so is this process 4,1. Here this is not isobaric. So the shape of the Carnot cycle is not as shown in your textbook. That is okay for a real gas, but if you have other systems, you can have all kinds of other shapes. Okay, so don't assume that the shape always looks like this. This is there for our convenience, this kind of shape. And you can have a Carnot engine and a fridge. A Carnot engine is a reversible engine. Why? Because it's made up of Carnot cycles. Carnot cycles are reversible. The same case for a Carnot fridge. Carnot fridge is a reversible fridge. So this is the same picture as shown in the previous slide, except that it's written here R indicating reversible. Okay, and there is only one specialty about this that is distinct. See, you have some values of QL, QH and W for a Carnot engine. If I reverse the direction of all these arrows, I will get a Carnot fridge. But it's not a question of only reversing the direction. The magnitude is unchanged. So that means this work exchanged, so the work output in a Carnot engine is exactly the same as the corresponding work input in a Carnot fridge. So I've written here that mod W, mod QL and mod QH are respectively equal for both cycles. So I mean that this heat extracted in the Carnot engine is same in magnitude as the heat rejected to the high temperature reservoir in a Carnot fridge. This is a specialty of a Carnot engine and a Carnot fridge. It is not the case in general. If I have a generic engine and I reverse the direction, I will get a fridge, but the values may not be the same. They won't be the same, in fact. I hope that is clear. So there is a clear distinction between a Carnot engine, Carnot fridge, and a heat engine and a fridge. Just a general heat engine and general fridge. Why? And of course, the reason is because a Carnot engine and a Carnot fridge is made up of reversible processes. A real engine and real fridge is irreversible, right? Made up of reversible, realistic things. Okay, so just remember that this is again an idealization. Carnot engine and Carnot fridges are idealized objects because, of course, they are made up of idealized processes called reversible processes. But we will use this Carnot engine, Carnot fridge for analysis, and we will use generally the Carnot cycle for understanding a lot of thermodynamics. Okay. So it's really useful, Carnot cycle, and it's useful because, as I said, the essential features of heat engines and fridges are encapsulated in a single diagram. You don't have to worry about the details of one engine versus another engine. We will do that, but that's hiding the basic facts within, hidden within. Okay, so this Carnot cycle in a way exposes the essence of a heat engine or a fridge. That's why we study the Carnot cycle. Okay, any questions? So we continue next week.